In this video we're looking at example question 7 and we've got 12 grams of naturally occurring carbon. Now we're given naturally occurring carbon basically includes carbon 14 and carbon 12. So these are two isotopes of carbon. The majority of naturally occurring carbon is carbon 12 and a very small amount of it is carbon 14. Now, if you look here, we're given the ratio of carbon 14 to carbon 12, and from that we can say that for every one carbon 14 nucleus in naturally occurring carbon, there are a trillion carbon 12 nuclei. That's in the American sense of the word trillion. So for every one carbon 14 nucleus, there are 1 times 10 to the 12 carbon 12 nuclei. And as a result of that, the carbon 14 nuclei, we can basically discount those when we figure out this first part of the question. So we can just focus in entirely on the carbon 12 nuclei because they're going to make up the majority of the mass of carbon, naturally occurring carbon. There'll be an absolutely tiny fraction of that mass being made up of carbon 14 nuclei, so we can just ignore it, which is handy. So let's get started here. So the first thing we need to do is we're going to calculate the activity of carbon 12 grams of naturally occurring carbon. Now, in order to do that, we first of all need to work out the number of atoms in this sample. So as I said, we're going to ignore the carbon 14 because it's such a tiny proportion of the mass. The first thing we need to know here then is for carbon 12, the mass of one nucleus of carbon 12 is equal to 12U. Because it's carbon 12, that tells us that the mass of one nucleus is 12 unified atomic mass units. To calculate the mass of one nucleus, because we know that the mass of one nucleus is 12 unified atomic mass units, all we need to do is convert that into kilograms. And to do that, we multiply by 1.66 times 10 to the minus 27, because that is the mass of one unified atomic mass unit in kilograms. So one unified atomic mass unit is 1.66 times 10 to the minus 27 kilograms. So 12 would be 12 times that, and that gives us 1.99 times 10 to the minus 26 kilograms. Okay. Now, to work out the number of nuclei in this carbon, in 12 grams of carbon, all we then need to do is take the mass of the entire sample, which is 12 grams, or 12 times 10 to the minus 3 kilograms, and we divide that by the mass of one carbon 12 nucleus. Remember, we're just ignoring the carbon 14 because it's such a tiny proportion. So 12 times 10 to the minus 3 divided by 1.99 times 10 to the minus 26. So if we take our calculator and input that, we're going to get 12 times 10 to the minus 3 divided by 1.99 times 10 to the minus 26, and that gives us 6.03 times 10 to the 23. Now, that number should be familiar to you because it's very close to Avogadro's number. The reason it's not quite is because we've rounded some of our values as we've gone through, but you should know, or you may know, that 12 grams of carbon, by definition, has 6.02 times 10 to the 23 atoms or nuclei in it. Okay. 12 grams of carbon contains 6.02 times 10 to the 23 atoms by definition, because that's used to define Avogadro's number, or 1 mole. Okay, it's used in the definition of 1 mole. 1 mole of substance is the number of atoms in 12 grams of carbon 12, and we know that there are 6.02 times 10 to the 23 atoms in 1 mole. Okay, so that's the first part of this question done. Now, the next part of part A is just to work out then the activity, and the activity is equal to A is equal to lambda n. Now that we know the number of nuclei in our 12 grams of carbon, we just need to take the decay constant and we need to multiply that by the number of nuclei. Okay, so it's going to be 3.83 times 10 to the minus 12, 6.03 times 10. That's going to give me 2.31 times 10 to the 12 becquerels. Okay, so for part B, we can say this. Originally, in natural carbon, you have a ratio of carbon 14 to carbon 12 of 1 times 10 to the minus 12 to 1. And then we found an old tree in a peat bog. This has a ratio of carbon 14 to carbon 12 of 0.34 times 10 to the minus 12 to 1. Okay, so you can see that the amount of carbon 14 in the old tree is less than the amount of carbon 14 in naturally occurring carbon. And the reason for that is the old tree has died, it no longer takes in carbon, so the carbon 14 has decayed within that tree and there's now less of it in there, okay? Living things take in carbon, so the ratio of carbon 14 to carbon 12 remains roughly constant, because even though this is decaying, it gets replenished. Dead things don't take in carbon, therefore the amount of carbon 14 decreases as it decays and becomes stable, okay, or decays into a different isotope or element. Now, what we need to do here then is recognise this. Because we're comparing the amount of carbon 14 to the same amount of carbon 12 all the time, it's something to 1, you can see that the carbon 14 has decreased. So you can see here that the amount of carbon 14 that we've got here has decreased by 66%. Okay, 66%, because it's gone from 1 times 10 to the minus 12 to 1 to 0.34 times 10 to the minus 12 to 1. So it's decreased by 66%. Okay, so therefore we can use this equation now. We can use the equation n over n naught equals e to the minus lambda t. And we can say that n is 0.34 times 10 to the minus 12, and n naught is 1 times 10 to the minus 12. Okay, so n equals 0.34 times 10 to the minus 12, and n naught equals 1 times 10 to the minus 12. And that is equal to e to the minus lambda t. Okay, so that's the equation that we've got now. We already know lambda, so all we've got to do now is natural log both sides. So 0.34 times 10 to the minus 12 over 1 times 10 to the minus 12 is just equal to 0.34. So we're natural logging that side. And if we natural log this side, we're going to get that. Okay, because log to the base e of e to the minus lambda t equals minus lambda t. So therefore we can then go up here and say this. ln 0.34 is equal to minus 3.83 times 10 to the minus 12, because that's the decay constant. Okay, sorry, not becquerels, should be seconds to the minus 1. So it's 3.83 times 10 to the minus 12 multiplied by t, and therefore t is going to be equal to ln 0.34 over minus 3.83 times 10 to the minus 12. Okay, now if we work that out, we're going to get this ln 0.34 over minus 3.83 times 10 to the minus 12, and that gives us 2.82 times 10 to the 11 seconds. Now you can convert that into years, obviously, so if you wanted to convert that into years, you would divide this by 365 times 24 times 60 times 60. 8942.16 years.